Uh, Hi, I'm Sivis Lagouvardos. I'm a PhD student at the University of Athens, and I'll be presenting our paper on Elipmoc, which is joint work with Neville Grech, Ilias Tsatiris, and my advisor, Yannis Maragdakis. And we all also work at DDOP doing program analysis for the Ethereum space. Now, Ethereum is a programmable blockchain, meaning that smart contracts, which are small programs, can be deployed on it. And these programs run on the low-level bytecode of the Ethereum virtual machine. Most of these are written in high-level languages, and Solidity is by far the most popular language. And because these contracts are deployed on the blockchain and everyone can interact with them, and their nature is often financial, and generally there's generally a high need for security guarantees. So we need to use all the tools we have to ensure that these contracts are safe and not hacked. So some background on the Ethereum virtual machine. It's a stack-based VM, and it doesn't have any information on variables, so we need to resolve this, the variables that the stack operations use. It operates only on 256-bit numbers, so they're integers, so there's no type information. All other types are supported with low-level operations as well. It doesn't have any abstractions for public functions or private ones. So everything uses the same stack, basically. And to support this, the jump targets of the basic blocks can be dynamic. So I'll show an example of that later. I'll explain that better. And also because the code is deployed on the blockchain and stays there, compilers have a strong incentive to reduce the deployed code size, so they reuse low-level blocks whenever possible. Now, if the Ethereum virtual machine is so low level, one may ask, why don't we just analyze Solidity source? And there are many reasons why that is impractical as well. So most contracts don't have their source code available, although the more used ones and the most popular protocols do have their source code public. And major Solidity releases include breaking changes, which is always a problem. And popular projects can use Solidity versions that can be from 0.4 to 0.8, and one would need to support all of this. And as also shown by the previous talk, widespread use of inline assembly means that source code tools need to model the low-level intricacies of the EVM and also the Solidity compiler sometimes, in order to support many behaviors. So that's a problem as well. Now, let's look at a simple smart contract. The contract looks like a class in object-oriented programming. Now, we have one field, and that field is stored on the blockchain. And in our case, it's the owner field. There's a constructor which sets the owner field to whoever initialized the contract, and an external method which is able to be called by anyone, but only allows the owner to withdraw funds from that contract. In addition, because the owner field is public, there will be a getter for that as well. So it's a pretty simple contract, but compiling it looks like this. Now, it's trivial to go from the compiled version to a disassembled version, which is that. And as we said, the contract has a single entry point. So in order to support the public function entries, we need some low-level code, and this next block just does exactly that. The entry point is decided based on the first 4 bytes on the transaction's payload. So this block does exactly that. It loads the first 4 bytes and checks them against a known signature hash, which is how this is done. Now, I'll talk more about this later. We can see another block which pushes 2 jump destinations to the stack and jumps to one of them, but leaves the stack with the other jump destination on it, which is also important, and I'll talk about more for that later. And we have another block which we can see that when looked at in isolation, we cannot really we cannot see what its target will be, what its next block is. So these are the dynamic jumps I was talking about earlier, and they are used very often to support code reuse. And and these make the compilation tough. So we need to model this. Now, let's give our definition of the compilation. So we define the compilation as the recovery of a structured intermediate representation, three-address code in our case, from very low-level bytecode. Now, so what we need to do is we need to infer the variables that the stack of operations use. We need to produce a control flow graph, and we also identify private functions in reused code segments and code reused in other ways. So one could ask that, don't we already have tools for that, academic or otherwise? Now, the most popular academic tool is Gigahorse, which is from a NIXI 2019 paper, but it has its problems. So it doesn't scale to large contracts because contracts have gotten exceedingly large as time went on and the Ethereum ecosystem progressed. Its output can be often imprecise, and it makes many mistakes when inferring function boundaries and argument and return argument numbers. So it can end up putting blocks in wrong functions. Now, now we present Ellipmoc, which is actually Gigahorse 2.0. It has been under continuous development since the original publication. It's open source and available on GitHub. And we use it at DDoP as a substrate for all our analyses. And we have decompiled and analyzed all contracts on the Ethereum and Phantom blockchains. Now, I'll give a brief overview of the common pipeline of Elipmoc and Gigahorse, and then talk about where we made some changes to that. Now, first we get the bytecode, we disassemble it, identifying the basic block boundaries. Then we perform a simple local, which means block level in our case, stack analysis. So we produce block level summaries for the effects each block has on the stack. We identify static and dynamic jumps, and we also identify the public entry points. Now, after this point, we use the information from the local analysis to perform a global control flow graph and stack analysis. Now, for this, the meaning of this is to resolve the targets of the dynamic jump statements, and to do that in a precise manner. In order to, because we don't attempt to actually execute the contract, we attempt to over-approximate all its behaviors using context sensitivity in our case. And this allows us to separate the different uses of the same block for different paths. And then after we have this global control flow graph, we go on to the next stage and try to infer private functions. And then after we have that, we generate our three-address code intermediate representation. Now, the output of our three-address code looks like that. So you can see that we have resolved variables statements to the variables they use and the ones they define. But it's still rather low level, but it's a good representation to have analysis on. And also something interesting here is that you can see that we have code reuse, we have private functions even in this small getter. So this function is a getter for the storage field. Now, what are our main contributions here? We introduced a new context sensitivity model, a transactional context sensitivity, which is designed after the execution of smart contract transactions. And I'll get into more of that later. And we also did some major improvements to the function reconstruction logic. We designed it and we made it context sensitive and path sensitive in cases in order to strike a good balance between precision and scalability. Now, a notable client we have on Elipmoc is source and parser, because when someone thinks of decompilation, we don't often think of what we define as decompilation. We also need a client that produces something that is more easily understandable by humans. And how we do that is we take the output of Ellipmoc, the 3 address code. We use some libraries that are available on our GitHub for inferring high-level instructions in memory and storage. And then we lift this into an AST representation, we perform simplifications on that, and we get the decompiled source. Now, the output of that for this particular contract looks like that. So you can see we have the two public methods on the left, and on the right, it's the function selector logic, which chooses the correct public function for the contract, and we use it for completeness in our output. Now, it's a simple contract, so our the compilation output looks very close to what is the source, but generally we do a good job. Now, I'll get into transactional context sensitivity a little bit more. So, the original Gigahorse publication had a call site, or a better name would be jump site in this case, context sensitivity algorithm, and we replace it with a domain-specific one that is composed of two parts. Now, the first one is a sticky public function context component, which essentially means that we keep the entry point of the contract, the transactional entry point, for the whole execution. And then we have a component that is parameterizable and contains the n most recent likely function call or likely function return sites. Now, we use heuristics for this because we cannot have a ground truth for that. So the likely function call sites are blocks that leave the stack with other jump tests on it. And the likely function return sites are the dynamic jumps I talked about earlier. So if we go back to our disassembled example, the first one is the code that finds the public function entry point, which we keep. The second one of the highlighted ones is a likely function call, what our heuristic detects as a likely function call, and it's important for us. And the third one is a likely function return. Now, what's important is that these do not always correspond to actual calls and returns, and the control flow is often much more complicated. So we can have like continuations where we can go from a return to another return, or from a return to another call, etc. So these are just an approximation, and in practice we've seen that it's a good model for context sensitivity. Now, we have an example here for an execution. Now, we have basic blocks on the left, and on the right there's a legend. So these blocks can either be single blocks, public function entries, likely function entries, likely function returns, and that actually. So the bold arrows are the ones that we keep in our model of context sensitivity. So let's take this execution on the left. We can see that we enter through the public function entry, and this is some information that we keep throughout the whole execution. But then the next few jumps, our analysis does not keep them in. We keep some information about them, but not in our context sensitivity for the global analysis. And then you can see that close to the bottom, we read some likely function call with here to this entry, which we remember, and then after another jump, a return, which we don't remember, a return as well. Now, in this case, we have a transactional context sensitivity depth of 2, so we'll only remember these two blocks. Now, this is not always good because, for example, if there were 7 different paths to reach these two blocks from the same public function, we would merge the information about all these together, which can lead to us having a precision, but it's something we are willing to live with. And called jump set sensitivity, as in Gigahorse, would try to remember everything up to its designated depth as well, which often keeps information that is not really important. Now, I will not get into the changes we made to the function reconstruction much, but you can check out the paper. I'll just mention the key points. Now, we added support for optimized recursive call patterns, and we did that context sensitively. So we try to keep all the information context sensitively and get the most out of our global analysis for our private function reconstruction one. Then we normalize control flow, which was a problem that Gigahorse had, and we find blocks that are shared between different private functions and we clone them to each one of them. So that's an improvement. And we have a path-sensitive argument and return argument inference algorithm. Now, for our evaluation, we evaluated the Ellipmoc against two tools. One is Gigahorse, which is its predecessor, and this was a very easy comparison because these two tools share their core. So this allowed us to make a very deep point-to-point comparison. Then we compared against Panoramics, which is the leading industrial decompiler. It is used by Etherscan, which is the most popular block explorer for Ethereum. And it's a very different tool. It is based on symbolic execution. It doesn't produce a control flow graph or any structured IR, really. It produces a source-like output, just like our source and parser. So we need to come up with high-level metrics. So for comparing against Gigahorse, we did it at a few points, like these are some of them. In the paper, we have more. We used the Gigahorse, Elipmoc, and second invocation of Ellipmoc, which uses the same context sensitivity as Gigahorse, and this helps us show and understand which of the benefit comes from the context sensitivity and what comes from the better private function inference algorithm. Now, the first thing we have is unstructured control flow. So unstructured control flow is basically at the output level of our analysis, control flow patterns that cannot be translated to high-level control flow of source code. Now, we can see that for Gigahorse, in at least 47% of the contracts decompiled by all tools, we have this problem, where in Elipmoc, we only have it in 8.8%. Now, as we can see using the middle bar in this graph, the main benefit came from the better private function inference algorithms. Now, polymorphic jump target is imprecision at the global analysis level, which basically means that under the same context, you have more next blocks. And we can see that Gigahorse and the context sensitivity of Gigahorse has this problem in close to 39% of contracts. The Ellipmoc context sensitivity, transactional context sensitivity, has it in under 12%. So it shows that our context sensitivity is much more precise. And looking at timeouts, Gigahorse times out in 18.7% of the contracts, while Ellipmoc times out in under 5% of the contracts. And you can see that this benefit comes again from the transactional context sensitivity. So it's both more precise and it has much more condensed information. So it allows us to be far more scalable. Now, getting into these scalability numbers in more depth, we can say that, so what we did here is we broke the contracts into, we split them into some classes based on their size, and we saw how well a contract does, a tool does, its success rate for these different sizes. Now, what we see here is that for larger contract sizes, say contracts over 15 kilobytes to up to 20 kilobytes, Elipmoc can decompile 86% of them, where Gigahorse can only decompile 42% of them. And for contracts over 20 kilobytes, Elipmoc can decompile 89% of them, where Gigahorse can decompile under 20%. So we are far more scalable in realistic contracts, and that's important because as the ecosystem becomes more mature, contracts become and compilers optimize more. Contracts become harder to decompile and analyze. Now, for comparing against Panoramics, we compared the output of our social parser client with that of Panoramics, and we had to choose some very high-level, contract-level and high-level metrics. So what we did was we chose the number of unique external call signatures, so the signatures to external calls made inside the contract, and the number of unique event signatures inside the contract as well. Now, we don't need to look into this in huge detail, but what I need to mention is that we used two different invocations of Panoramics. The one was with is a default with the same timeout as we gave to Elipmoc, and we used the partial invocation of Panoramics as well, which allows it to time out for certain public functions and continue if it failed for them. And for that, we gave it 2.5 times the timeout of Ellipmoc, and it still didn't manage to scale as well. And we can see that Ellipmoc is both more complete and more scalable than Panoramics. And we also, at the bottom two rows, we we provide numbers for the intersection of contracts that both of these tools analyze, and we can see that Panoramics takes 10 times more time and is less complete. Now, we perform the same experiment to get into the scalability in more depth, and we can see that Panoramics has a similar behavior to that of Gigahorse, and it is way more unscalable for larger contracts. So we've used the Ellipmoc to build several research tools on top of it. The first one is Ethainter, a smart contract security analyzer for composite vulnerabilities, which was presented in PLDI 20 and will also be presented tomorrow at 4:30 at seminar room LG004. Our OOPSLA 20 paper on the precise static modeling of memory, and our OOPSLA 21 paper on the symbolic value flow static analysis, which will be presented at 12 today at seminar room LG004 again. Something that is worth mentioning is that we've used Elipmoc to perform 3 studies for the Ethereum Foundation, assessing the impact of some protocol changes to all deployed contracts, and these are EIP 1884, EIP 3074, and future change that is proposed to change the gas system of Ethereum to use vertical trees. And we also use it on contract libraries Watchdog, on DDoP Watchdog, to perform security analysis, and these have gotten us 7 high-impact vulnerabilities in popular protocols. So thank you for your attention.
Okay, we have a lot of time for questions. Yeah, go ahead.
Cool, thanks. Nice talk. So I actually had I think it's a simple question. Because you said, obviously control flow can be quite unstructured and does get quite complicated, but I'm interested in particular in whether or not bytecode generated from the Solidity compiler is much more structured and easier to decompile versus arbitrary bytecode.
I mean, we don't often see arbitrary bytecode. Most of it is from a Solidity compiler, either the Viper compiler way less, and we don't really know what other thing there is, because there are some contracts where they look like it doesn't come from the Solidity compiler, but they don't have the source code available, so we cannot really understand. But these are very few. And what I think is that they are contracts that make heavy use of inline assembly. And someone starts from something that is generated by the Solidity compiler and then tweaks it by hand to be more optimized or whatever. But I don't really have.
So, sorry, just trying to. So, if we imagined a contract, Solidity contract with no inline assembly, compiled using optimization with a Solidity compiler, that is not the hardest kind of code to decompile.
Oh no, it is
Still hard.
It's very hard, yeah.
Okay, thank you.
Thanks for your presentation. So as you have shown, you have a lot of intermediate steps in your analysis. Do you have APIs that expose these intermediate results in a way that is really convenient and makes it possible for other analysis tools to build on this? Or you mentioned some cases of other analysis tools that build on it, but is this kind of at the end stage, or is it a very internal integration, or are you moving towards maybe sort of standardized interface for, say, exposing the control flow structure to other analysis tools that then other people might build?
We don't really have an API for that, but what we have is the source code, so everyone can run Gigahorse and get the IR we produce, and also use some other libraries. Now, we don't have the source code available, like the source compiler available, but for the Dimitri presentation for analysis, it's all there. It's all on GitHub. So that's what we have available.
Yeah, maybe going a little bit beyond your topics, but if you look at the scalability result table again, it wasn't really a clear dependence. Of course, clearly dependent on the sizes. Not yet this one. Yes.
Yes.
So I was curious about the remaining 10% beyond that 20 kilobyte. Is that all the sheer size, or what? Can you elaborate on what makes you unable to decompile certain contracts?
Okay, so for our tool, right? For Elipmoc.
Yes, of course.
Yeah, it's mostly cases where something in our analysis becomes unscalable. So some patterns, perhaps, where we have our abstraction for context can end up producing many contexts and many inferences that are not perfect, so have some unscalability there. And also the private function inference is which takes that the context sensitivity can also become very unscalable sometimes, because it tries to be path sensitive. It tries to infer lots of information context sensitively. So this is the main reason. It's,
so it is scalability.
Yes, it's scalability.
This is a very nice work. Thanks for the talk. Actually, I wanted to ask, can you go back to the slide where you show the different basic blocks with the edges? This one. So over here, so when you say this is a likely private function entry, right? So how many of these? How many of these do you consider when you are like constructing the control flow graph? Like, so how do you figure out that? Okay, I mean, like these are the blocks in the function, like, or these are the possible jumps that are happening.
So we consider all of them. Basically, it's a very simple heuristic, and that heuristic is that any block that looks like the middle one there, that pushes that leaves a stack with another jump destination pushed to it, we consider it to be a possible call, and for our context sensitivity, it's a possible call. So we don't try to bind that.
Okay. So, in case if there are functions that are like, so can it happen inside the bytecode where like functions are sharing blocks between them or blocks of code between them? So,
Yes.
in that case, how do you like construct the control flow graph for, let's say, a particular function?
What we do is we basically, like, after we figure out that a block is part of more than one function, we clone the blocks in both functions.
So, can it so happen that like when you are cloning, like can the context change? Like, I mean, the things that are there in the stack, like, so how do you fix that in the function? So, can it so happen that like each of the functions, like, do you check that the stack contains like the same elements, like when you are cloning the blocks?
I do not understand the question, sorry.
So,
Okay, let's move this offline, all right?
yeah, I think I'll probably take it offline. Yeah.
Okay. All right, yeah, let's thank speaker again.